Hello, this is review of Unit 1. We're going to start talking about our rules of exponents. When we multiply with like bases, remember we're just going to add our exponents together. We would have x to the 10th because there's an assumed 1 there. When you raise a power to a power, we multiply. If you have several parts of your term being raised to an exponent, you have to remember to apply everything to that exponent. So 2 cubed, we would have 8. Y squared and then cubed would be y to the 6th. Z to the 3rd would just be z to the 3rd. With fractions, make sure you're applying that exponent to both numerator and denominators. So here we would have x to the 9th. All over 4 cubed is 64. Y to the 2nd raised to the 3rd would be y to the 6th. When we divide with like bases, we're going to divide our coefficients like we normally would, so we'd have 6. But when dividing with those like bases, we just subtract those exponents. We'd have x to the 5th, y to the 2nd. When we add polynomials, we're just combining like terms. So we're adding x's to x's. I'm going to have 12x here, negative 4y and 6y, that's going to give me plus 2y. And minus 2z and minus 9z gives us minus 11z. When you are subtracting your polynomials, we're distributing out our negative or doing keep, change. So that becomes addition. That becomes a negative x squared. That becomes a plus, and that becomes a minus. Now when I combine my like terms, 2x squared minus x squared just gives me x squared. Minus 5x and plus 9x gives me plus 4x. And then the minus 2 comes along. When we multiply, we're just going to distribute. So remember, when we distribute, that applies to all the terms. We would have 2x cubed minus 10x squared. Those can't be combined because they're not like terms. When we FOIL, we distribute the first term and the last term. Our first term would become 18a squared. 6a times 4, that would give us plus 24a. Minus 6a, and then minus 8. Then we're just going to combine like terms. We have 18a squared plus 18a minus 8. I'm not going to actually do this one, but when we do have a binomial squared, we would have to write that out twice and FOIL it. But hopefully by now we're pretty comfortable with the foiling. So I'm just going to jump to the next section. When we are proving our polynomial identities, we want one side to end up looking like the other side. For this one, I'm going to cube this binomial, which means I'm going to have to write it out 3 times. X plus y times x plus y. Now I can only multiply 2 binomials at a time, so here I'm going to FOIL the first 2. We would have x squared. We would have an xy and another xy that's going to combine to a plus 2xy and then plus y squared. We're going to take that whole trinomial and we're going to multiply it to the remaining x plus y. From here, when I multiply these, I would get an x cubed plus x squared y plus 2x squared y plus 2xy squared. And then when I distribute out the y squared, we have plus xy squared plus y cubed. So again, my goal is for these two sides to look the same. They're getting there. I just now have to combine like terms. X cubed first, then I'm going to combine my x squared y's. I have those terms there which combine to plus 3 x squared y. And then I'm going to combine my xy squareds. That's those and those. That's going to combine to another plus 3 xy squared, and then plus y cubed. Now I've successfully made this to look like this. So I've achieved my goal. I've proven that identity. Next, we're dividing a polynomial by a single term, which is known as monomial. I have to divide each of those terms. So if I divide 25x cubed by 5x, we get 5x squared. Dividing my middle term by 5x, to have minus 3x, and dividing those last two terms, 5x divided by itself, we do have plus 1 there. Make sure you're not just canceling out those terms. A lot of students will cancel those out, but those cancel, yes, but they really cancel to a 1. Next, we have our synthetic division. For synthetic division, you're going to take the 0 of the divisor. That just means what you're dividing by. If you were to set that equal to 0 and solve, we'd get x equals -5. I'm going to put that in what we call the corner. And then we're going to take our coefficients, and the coefficients are 1, 2, -14, and 4. At that point, I bring down the 1, I multiply, add straight down, and I multiply. Multiplying by the number in the corner, and then when I add straight down, again multiply, add those together, we get -1. Now -1 is our remainder, that last term. It's always your remainder. The other terms are just our coefficients. The other terms are the coefficients of our answer. We're going to have 1x squared. I know it's an x squared because I take 1 away from that degree, 1 away from that exponent, minus 3x plus 1, and then plus remainder over divisor, plus -1 all over x plus 5. If you don't have that 1 out front, that's perfectly fine. I just wanted to make sure you were clear on where that was coming from. Next, we're going to take that same problem. However, we're going to divide those using long division. With long division, we take the divisor, we put that out front. We take what we're dividing, we put that underneath. So we take the quotient of our leading terms, or we say x times what is x cubed. We'd get an x squared. We're going to distribute out. We get x cubed plus 5x squared. At this point, we're subtracting. So I'm going to distribute out my negative, or do keep change. So the subtraction becomes addition, that becomes negative, that becomes negative. Those terms on the left should cancel out if I'm doing this correctly. We'd be left with -3x squared, and I'd bring down the minus 14x. We're going to divide the leading terms. I'd say x times what is -3x squared. We'd have a minus 3x. I'm going to distribute out, just like I did previously. We would get minus 3x squared minus 15x. Again, we are subtracting. I'm going to do my keep change all those signs. Terms on the left should cancel out. we'd have positive 1x, or just x, and then I drop down the plus 4. I divide out the leading terms. I say x times what is itself. That would give me a positive 1. I'm going to distribute out my 1, again to both terms. We'd have an x plus 5, and then I subtract. Distributing out the negative. Combining like terms, those cancel out. We're just left with a negative 1. Now that negative 1 is my remainder, so I'm going to again write that as plus remainder over divisor. Next is the factor and remainder theorem. And we're given the image of a function f of x, and we're trying to determine the remainder when f of x is divided by each of these 3 terms here. So what we're going to do is, again, we're going to take the 0 of these divisors. If I were to set that equal to 0 and solve, I would get x equals 2. I'm going to evaluate for that term. If I find f of 2, I go over to my graph. I go to where 2 is on the x-axis, and I go to the function, and I'm actually right on the function, so the corresponding height at that point would be a height of 0. For the next one, we would be looking at evaluating for f of negative 1. And if I go to negative 1 and I go up, I'm at a height of 4. Last, for x, if I were to find the 0 of that divisor, it would just be x equals 0, so I'm evaluating for f of 0. At 0, I'm actually on that function. Corresponding height then, again, is 0. When we simplify radicals, anything that's not a perfect square, we want to split it up. We would want to find the largest perfect square that divides evenly into 75. That would be 25. 25 and 3. X to the 14th is an even exponent, which means it's a perfect square. Our even exponents are perfect square because they're divisible by our index, which is 2. Y to the 11th, that's not a perfect square. If I take one y away, I'm left with an even exponent, which again is a perfect square. So if I square root that first term, I'm left with 5 x to the 7th, y to the 5th, just dividing that exponent by the index, and then I bring along the radical that could not be simplified. When you're simplifying perfect cubes, again, we want to split it up if it's not a perfect cube. I know 54 is not a perfect cube, so if I were to write out my perfect cubes, well, 1 cubed would be 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and so on. So 54 is not a perfect cube, but it is divisible by 27, and 27 is the largest perfect cube that would divide evenly. It would be 27 times 2. X cubed is a perfect cube because, again, that exponent is divisible by the index. Y to the 14th is not a perfect cube. If I take one y away from it, I'm left with y to the 13th, which is not a perfect cube. But if I take 2 y's away, if I take away a y squared, then I'm left with y to the 12th, which again is a perfect cube. So if I cube root 27, we get a 3. Cube root of x cubed is just x. Cube root of y to the 12th is y to the 4th. And then you just bring your other term down. And that's it. It's fully simplified. Next, if we were to add and subtract some radicals, we need to, again, have like terms. So I'm going to have to simplify each term individually. X to the fourth is a perfect square, but y itself is not. So I'm just going to organize these before I simplify them. Same thing with the next term. X squared is a perfect square, so I'm going to put that under its own radical, but y is not. So now I can simplify my perfect squares. The square root of x to the fourth is x squared. The square root of x squared is just x. And now I can clean up my remaining terms. I'm left with 5x squared, radical y, plus 2x times x gives us 2x squared, radical y. Now I do have like terms, so those can be combined. When I add those together, we get 7x squared, radical y. When you are multiplying radicals, you do not need like radicals, so I can just distribute those two terms out. When we multiply the coefficients. 3 times 2, we get a 6. Radical 3 times radical 2, we get a radical 6. When I multiply my next step, this coefficient, if you don't see it, is assumed to be 1. Multiplying the coefficients together, 3 times 1, we get a 3. Radical 3 times radical 4, we get radical 12. Those are not like terms, but I can simplify the radical 12. Radical 12, I can even do this off to the side. I know it's going to split up into a 4 and 3, which would give me 2 radical 3. So I can replace that with times 2 radical 3. Then we end up with 6 radical 6 plus 6 radical 3. We don't have like radicals, so that's as far as we can go there. Our answer is just a binomial, and that's okay. They won't always combine. Next, when we divide, you have to divide both of those terms by the denominator. So the quotient of the first set of terms, that would give me 5. Radical 9. Quotient of the next terms would give us 5 divided by itself would give us a 1. So then we're just left with radical 4. We have some perfect squares here. The square root of 9 is a 3. The square root of 4 is a 2. And then just remember you're multiplying. So 5 times 3 would give us a 15 plus 2, which that combines to a 17. When you are dividing with radicals and you've simplified everything as far as you can't leave a radical in the denominator. So in order to do that, we're going to rationalize. When we rationalize, we're just going to multiply by that radical over itself. We don't care about the 3. We can leave that. It's just the radicals that we don't like and we need to get rid of. So multiplying straight across, we'd have 3 radical 2 all over 3 radical 2 times itself is just 2. And then we can multiply from there. We'd have 3 radical 2 all over 6. And then we just want to reduce. 3 goes into itself once, into 6 twice. So we're left with radical 2 all over 2. When we rationalize with binomial denominators, we have to multiply the numerator and denominator by the conjugate, which in this case would be 2 plus radical 2 all over itself. So when I distribute out on top, I'm left with 12 plus 6 radical 2. In the denominator, multiplying the first terms and last terms, I can do this because they're conjugates of one another, and I can use that shortcut. When we multiply those, we're left with 4 minus radical 2 times radical 2 is just 2. I can clean that up. 4 minus 2, that gives us a 2. Now we have to divide each of those terms in the numerator by the 2. We would end up with 6 plus 3 radical 2. Those are not like terms, so that's as far as I can go. And then our last problem says find the value of m so that when we divide these terms, we're left with a remainder of 270. So what we can do again is take the 0 of the divisor, which means I take that x plus 5, set it equal to 0 and solve. We get x equals -5. And I'm going to plug that in everywhere I see an x. So we'd have m times -5 squared plus 2 times that -5 plus 3m. So I'm leaving m as m. And then when I do that, that will equal the remainder. And from there, we're just solving. If you square -5, we get positive 25. That gives us 25m minus 10 plus 3m equals 270. We combine to get 28m minus 10 equals 270. Adding 10 to both sides gives us 28m equaling 280. Dividing 28 on both sides, we are left with m equals 10. And that's it. If you have any questions, make sure you see your teacher.